All right. So, in the previous lecture, we had discussed the cascode, right? And then we also said that we will talk about current mirrors in the today's lecture. So, let us talk about the current mirrors. So, in the previous lecture itself, we said that if I have a current source, for example, IREF, so which does not vary with supply voltage and temperature. Okay, so this is a very good current source that does not vary with supply and temperature. So I now need to copy the current of this current source at various locations on the integrated circuit. And this circuit which copies this current is called current mirror. Okay, so this is what we commented in the last lecture. So let us now know what is this circuit current mirror. So this is my current mirror circuit. A little bit I'll zoom it. Okay. So a current mirror circuit consists of a reference transistor, okay, QREF, and in this reference transistor, the collector and base, so they are both tied together. Okay. And then you have a current source over here. Now another transistor Q1 is attached base to base with QREF, okay, this transistor, and this current I copy 1. So this is equal to IREF. Okay, that is this current is copied here on this transistor Q1. Okay. Now this current can be used anywhere on the chip for biasing some other transistor. Okay. Now this I copy 1. So I want this I copy 1, that is this current, to be equal to the reference current. Okay. And I also want this, I mean, considering that IB is negligible, that is this current coming into the base, okay, so this is negligible, then this IREF would be equal to the current through the collector of this reference transistor. So if the current going into the collector of the reference transistor is, let us say it is IC ref, that is collector current of reference transistor. Okay. So this collector current of reference transistor will be equal to the reference current only when IB is negligible. Okay. And in this current mirror, since I want I copy 1 to be exactly equal to IREF, okay, so this is only possible when these two transistors are identical. That is Q1 has to be identical with QREF. Otherwise this I copy 1 will not be equal to IREF. Okay. So these two transistors need to be identical. Okay. So why they need to be identical? Let us understand by performing some analysis on this circuit. Okay. So I can write this potential Vx. Okay. So if I can write IC ref, okay, so I can write IC ref, for example, IC, that is collector current of reference transistor. Okay. So using the diode equation, okay, that is collector current through the diode equation. So I can write that collector current is equal to saturation current, okay, multiplied by e to the power VBE by VT. Okay, so this is what we had studied earlier, that collector current can be written in a BJT by referring to the diode current. Okay. So collector current IC ref is saturation current of reference transistor multiplied by e to the power VBE. So VBE here is Vx. Okay. So I'll simply replace this VBE by Vx. Let us say Vx instead of VBE. Okay. So collector current is now IC ref is IS ref e to the power Vx by Vt. So from here Vx can be found. So Vx can be written as Vt log, okay, Vt log IC ref by IS ref. Okay. So I can find out Vx, that is this node potential, Vx. Okay. And we have already said that IC ref is equal to I ref since IB is negligible. So let us say this is I ref only, not IC ref. Okay. So this is I ref only. Okay. So which is written over here. So this Vx is equal to this much. Similarly, I can write I copy 1, that is collector current through this Q1 transistor, okay, by using the same diode equation for this transistor. Okay. So from here I can write I copy 1 is equal to IS of transistor 1 multiplied by e to the power Vx by Vt. Okay. So from here I can write Vx. Okay, so Vx is Vt ln I copy 1 divided by IS1, saturation current of transistor 1, okay, which is similar to this equation here. Okay. So Vx is equal to this much. Okay. So from here, I mean both these Vx are equal, so I can find out from here, I mean this goes off, this also goes off. Okay. So I can find out I copy 1 from here. So I copy 1 is IS1, it will go here, divided by IS ref multiplied by I ref. So this is the current that we get through this current mirror circuit. Okay. Now this current I copy 1 will be equal to I ref. Okay. So these two will be equal here, that is I copy 1 will be equal to I ref when the saturation current of both these transistors are equal. Okay. Or in other words, if these two transistors are identical, then only these two will be equal. So if they are equal, then I copy 1 will be equal to I ref. Okay. That is, this copy current will be equal to the reference current. Okay. So that means 100% mirroring. Okay. So 100% mirroring is only possible if both these transistors are identical. Okay. Otherwise, this will not be 100%. Okay. Okay. Now this is not a current mirror, okay, because this collector is not shorted here to the base, so there is no path for the base current to flow. Okay. So I copy will be 0 in this case. Okay. Now one can generate multiple copies of IREF, right? Not just one copy, a second copy, a third copy, or maybe a fourth copy, right? So they can be generated by simply connecting all the bases of the transistor, okay, together, okay, and so on. Right. So multiple copies of this reference current can be generated. Okay, that is, I copy 1 can be equal to copy 2, copy 3, copy 4, which is equal to IREF, okay, by using the same concept. So one can write a general equation for current, that is, I copy J is saturation current of J divided by reference current of, sorry, saturation current of reference transistor multiplied by IREF. Now let us say that this Q3 is not identical with Qref. Okay. So then that means that the I copy 3 will not be equal to Iref, okay, because the saturation current of third and reference BJT, so they will not be equal because the transistors are not identical. However, I copy 1 and copy 2 can be equal to Iref if Q1 and Q2 they are similar to this transistor, reference transistor. So if these are identical, the saturation currents will be equal, okay, and the copied current will be equal to the reference current. Okay. So it is possible to generate the same current. I mean, this current, that is maybe I copy 3. So this can be greater than Iref also and can be less than Iref also. Okay. So depending upon this ratio. If saturation current of third transistor is larger than the reference transistor saturation current, then I copy can be larger than the reference current. So scaling up and scaling down of the current. So both are possible. That is scaling up and scaling down of the current are possible. Okay, through this ratio of saturation current. Now saturation current depends upon again the transistor size. Okay. We had seen that the current in a BJT is dependent upon the area of the emitter. Okay. So if I can change the area of the emitter, for example, the area of the emitter is AE, let us say, of QREF, and here if it is 2AE, right, twice the emitter area of QREF, then obviously the current here will be twice IREF. Okay. So maybe that is being explained here in this slide. Okay. Current is scaling. Okay. So let us say that the area of QREF transistor is AE. Okay, this is the emitter area. Okay. And Q1, Q2, Q3, all of these also have emitter area of AE. Okay. And the collectors of Q1, Q2, Q3 are tied together. Okay. So each will draw IREF. Yeah, each of these will draw IREF. So total current drawn here, that is I copy, will be 3 times IREF. Yeah, that is fine, understood. Okay. Now we had also understood in our previous lectures that a BJT. Okay, so let us say I have a BJT with area, some area, emitter area AE, and I want a bigger BJT. So I want a bigger BJT transistor now, which has, let us say, twice the area, emitter area. Okay. So bigger means obviously emitter area is larger. So the bigger transistor can be created from smaller transistor by connecting the smaller transistors in parallel. That is tying their emitters, collectors and base. Okay. So this way one can achieve a bigger transistor. So this transistor now has a emitter area of 2AE. Okay. So now when it has a bigger emitter area, so it will draw larger collector current or emitter current. Okay. So that means these 3 transistors represent a single big transistor which has 3 times emitter area in comparison to the emitter area of reference transistor. Okay. So that means the current here will also be 3 times the current flowing in this reference transistor, and the current which is flowing in the reference transistor is IREF. So 3 times current will flow in this bigger transistor which has 3 times the emitter area. So current will be 3 IREF here. or one can write a generalized form of current over here, that is I copy J, okay, so will be equal to N times I ref. Okay. So three transistors, current is 3 times I ref. Okay. Or one could say that current is scaled up, okay, by a factor of N. Let us take some examples on the scaled currents. Okay. So here three transistors, okay, and the area of emitter area is AE of reference transistor, and for all these transistors Q1, Q2, Q3, Q4, Q5, all these have AE emitter area, right? Q1, Q2, Q3, Q4, Q5, all these have emitter area of AE. Okay, so three transistors here tied together, so total area of emitter is 3 AE. So the current also will be 3 IREF. Okay, so that is 3 multiplied by 0.25. Okay, so which is 0.75 milliamperes. Okay, so the total area drawn by this pair of three transistor is 0.7 milliampere. Similarly here 2 times emitter area, right? So that means 2 multiplied by 0.25, okay, current, okay, 2 IREF, or 2 multiplied by 0.25 or 0.5 milliamperes. Okay, so current here has scaled up. Okay, so here it is 0.75 milliampere, here it is 0.5 milliamperes. So through the current mirrors one can generate not only the same current but scaled up currents, and those scaled up currents can be different because in an IC you may require different values of current at different places, right? You have millions of transistors, so it is possible that all those transistors do not require same current for biasing. Okay, so different currents might be required for biasing, so those different currents can also be produced, okay, by either scaling the current up or down. Okay. Let us see another example where the current has been scaled down. Okay. So here we have three reference transistors, okay, connected in parallel together. So this represents a bigger transistor with area 3 AE. Okay. So here the area is 3 AE. I mean 3 times the emitter area of one transistor. Okay. So that means the current going into the collector of each transistor will be 0.25 by 3. So current going through each transistor will be I ref by 3. So this is the current in each of these transistors. Okay. And I copy will be equal to then the current which is drawn by the collector. Okay, so here in the previous case also the copied current will be equal to the current drawn by the transistor. Okay, so we had commented here that the copied current will be equal to, right, the copied current will be equal to the current drawn by the transistor. Okay, the current drawn by the transistor was IC ref, okay, not I ref. But here in this case, since we assume that the base current is negligible, so that is why I ref could be IC ref. So I copy event could be I ref. But in this case, let us go back here. In this case, there are three transistors, reference transistors. So each is drawing I ref by 3. Okay. So I copy will be equal to the current drawn by each transistor. Okay, not equal to I ref here. Okay. So then current drawn by this transistor Q1 I copy will be equal to 1 by 3 I ref, okay, or I ref by 3. If you place a fourth transistor over here in the reference transistors, then I copy will be I ref by 4, or the copied current has been scaled down. Okay. So we have scaled down the copied current. So let us take another example here. So in this example, reference current is 0.2 milliamperes and we have 4 transistors in parallel at the reference. So that is total emitter area is 4 AE. So each transistor will draw 0.25 by 4, that is 0.05 milliamperes. Okay. So that is I copy 1 if the transistor area is same, that is AE, right? Each transistor has an area of AE. So this transistor Q1 also has a area of AE. So I copy 1 will be equal to 0.05 milliamperes. Okay. Now let us say that this transistor Q2 has a area of 10 AE. Okay. So I copy 2 will be equal to 10 times this IC ref, that is 10 multiplied by 0.05, which is 0.5 milliamperes. And now so far we have assumed that base current was negligible. Okay. Now let us consider the effect of base current. Okay. So for considering the effect of base current, uh, we'll have to decide current going into this branch. Earlier we had assumed it was negligible. Okay. So current going into this branch will be Iref minus the current going into this branch, which is IC ref. Okay. So current going into this branch will be equal to Iref minus IC ref. Okay. So Iref minus IC ref. Okay. So this current is coming here also, Iref minus IC ref. Okay. Okay. Now the emitter area of Qref is AE and the emitter area of Q1, that is this transistor, is N times AE. Okay. So copied current, that is I copy, will be equal to N times the current drawn by the collector of this transistor, that is N times IC ref. Okay. Or from here I can write IC ref as I copy by N. Okay. IC ref is I copy by N. Let us say this is my equation 1. Okay. Now the current going into the base of this transistor. Okay. So this can be written because now I know I copy. This current is known, so I can write the base current, okay, by using the relation IC is beta IB. Okay. So using IC is beta IB, that is IC is beta IB, that is I copy is beta times IB. Okay. That is IB1, or I would say this is IB1. Okay. Or IB1 is I copy by beta. Okay. So I can write IB1 as I copy by beta. So that is this current IB1 is this much. I copy by beta. Okay. Similarly, the current going into reference transistor IB ref. Okay. So let us say this is IB ref by again using the same IC is beta IB. Okay. And IC here is IC ref. So IC ref is beta times IB ref. So from here IB ref can be found. Okay, so IB ref would be equal to IC ref by beta, and IC ref is I copy by N. So I put IC ref is I copy by N and beta remains over here. Okay. So IB ref is I copy by N beta. So 3 currents I know now. So one is this one, the other one is I copy by beta, third one is I copy by N beta. Okay. So I apply now KCL at this point. So apply KCL at this point. So I can write this current is equal to this current plus this current. Okay. Okay, that is I ref minus IC ref is equal to I copy by N beta plus I copy by beta. Okay, so I can write, so let us write I ref minus IC ref, this is equal to I copy by N beta plus I copy by beta. Okay, so I take this IC ref on the right hand side, I get this relation 2. Okay, just take IC ref on the right hand side. Okay, so I got equation 2 over here. Okay, now this equation has IC ref which is also present in equation 1 over here. So I put IC ref from here in equation 2. Okay, so IC ref is I copy by N. Okay, so I write I copy by N here. Okay, so using 1 and 2, that is, if I write I copy by N over here, so then this equation modifies to this, right? That is I ref is, I take I copy common, 1 by N plus 1 by N beta plus 1 by beta. Okay, so from here I can find out I copy. So I copy would be I ref by this term. Okay, or I copy could be written as N times I ref divided by 1 plus 1 by beta N plus 1. Okay, so this much is the current that is copied. Okay, now this current is not equal to I ref, obviously, that is I copy is not equal to I ref. Okay, so we were assuming that it will be N times I ref, but it is not N times I ref because beta is coming in the denominator. Okay, now, so that means this I copy is not 100% equal to N times I ref here. Okay, because of this beta. Okay, now if this term, this entire term can be made small, then one can say that I copy will be nearly equal to N times I ref. Okay, so how to make this small? If beta can be increased somehow. If beta somehow increases, then this term can be made small. Okay, so let us see how to make this term small so that the conversion accuracy becomes, or mirroring accuracy becomes good. Okay, so mirroring accuracy can be improved if I can reduce this term by increasing beta. So let us see how to increase the mirroring accuracy. So the mirroring accuracy can be improved if another transistor QF here is used. Okay, so instead of connecting the collector directly to the base, we uh, connect, or we make this connection via this transistor QF. Okay, now if I make this connection through QF, the mirroring accuracy can be improved. How it can be improved? So let us try to understand. So let us do some analysis on this circuit again. So let us write equation 1 first, which is I ref is IBF plus IC ref. Okay. Okay, so equation 1 one can write, that is I ref is IBF plus IC ref. Okay, and since this is N times AE, okay, so that means I copy should be equal to N times IC ref. Okay, so I can write this relation also 2, that is I copy is N times IC ref. Okay, then I can write third equation, uh, which is that ICF, in fact this ICF flows here also. Okay, so ICF is equal to IEF, right? So in fact we are trying to apply KCL at this point again. Okay, KCL, so that is this current which is equal to ICF or IEF, so this is equal to this current plus this current. Okay, So ICF is I copy by N beta plus I copy by beta. So this is third equation now. Now fourth equation I can write knowing that IC is beta IB, okay, for this transistor F. So I can write IBF as ICF by beta. Okay, and ICF I have already found here. Okay, so I can find IBF by simply dividing this by beta. Okay, so IBF is found here. Okay, okay, okay. Now IBF is found here. Now we'll put equation 2, 3 and 4 in one. Okay, so because IBF we got here, so which is required here, and ICREF also we have found here, which requires I copy. Okay, okay, so I can find out from 1 by putting this ICREF and IBF into this. So if I put, I get this relation, that is IREF is now equal to IBF. Okay, so IBF is simply this divided by beta square. I copy by this is n beta square. Okay, so this n plus 1 by n. Okay, plus I copy by n, and which then is equal to this much. I copy by n plus 1 by beta square plus 1. So from this I can write I copy. So I copy can be written as this much. So which is similar to this I copy. So both are same. Okay. So that is the current that is copied is now equal to this much. So here we see beta square in the denominator. In the previous case, we didn't have beta square here. Okay. And we said that if we can reduce this term by increasing beta, then mirroring accuracy will be improved. Okay. So here the mirroring accuracy looks improved because instead of beta it is beta square. So this term is further small. Okay. So I copy is now more close to n times IREF. Okay. So mirroring accuracy can be improved by this transistor QF. That means. Now for this circuit, let us say we have this circuit where we have 4 reference transistors connected in parallel, and we have QF also to increase mirroring accuracy, and then we have a emitter transistor here Q1 which has an emitter area AE, and another transistor Q2 which has an emitter area of 10 times AE. Okay, so now let us try to find out I copy 1 and I copy 2. Okay, so I copy 1 and I copy 2, let us try to find out. Okay. So for finding out I copy 1 and 2, I'll write equation 1 first, which is IREF is equal to IBF, okay, plus 4 times ICREF. Okay, because we have 4 transistors and in each transistor ICREF goes, so total collector drawn by the 4 collectors will be 4 times ICREF. Okay. Next we write equation 2, ICREF is equal to I copy 1, right? So for this transistor I copy 1, so this is true, that is I copy 1 is equal to ICREF. Okay. Now one can write for this transistor Q2. Okay. I copy 2 will be equal to 10 times ICREF because emitter area is 10 times the emitter area of one transistor here. Okay. So I can write I copy 2 as 10 times ICREF. Okay. Now from these two equations I can write a relationship between I copy 1 and I copy 2. That is, I copy 1 is I copy 2 by 10. Next, I will write equation number 3, which is this current ICF. So again, applying KCL at this point. Okay. KCL. So you apply KCL at this point. Okay. So KCL means this current will be equal to current going here into reference transistor, current going into Q1 and current going into Q2. So four currents we have here at this point. Okay. That is ICF or IEF. Okay. So ICF is equal to the current going into this is I copy 1 by beta. I copy 1 by beta. Okay. Current going into this is I copy 2 by beta. And current going into the base of this reference transistor. So this should have been IC by beta, IC ref by beta. Okay, so this base current should have been IC ref by beta. But since there are four transistors connected here, so this current going into the base of four transistors would be 4 times IC ref by beta. Okay. So I write equation 3 here now this way. Okay. Now from this relation, okay, I mean I copy 1 and I copy 2 I can write in terms of IC ref. Okay. So I copy 1 in terms of IC ref, I copy 2 in terms of IC ref. I can put I copy 1 as IC ref and I copy 2 as 10 times IC ref. Okay. So this will give me this equation 4. Okay. I copy 1 is IC ref, I copy 2 is 10 times IC ref and 4 IC ref by beta as it is. So this gives me the collector current through transistor F as 15 IC ref by beta. Okay, so this is, let us say, equation 4. Okay. So collector current ICF, so this is known to me now. Now I can write IBF. Okay. By knowing again IC is beta IB. Okay. So I can write IBF as ICF by beta. ICF is known from here, which is 15 by beta. So IBF will be 15 I copy 1 by beta square, because IC ref is I copy. Okay. So I get equation 5. Okay. Now from equation 1, that is this, 2 and 5. Okay. So from these three equations, 1, 5 and 2. Okay. That is, one is this IREF. So I'll put IBF, that is obtained here, here, and ICREF, which is I copy 1. Okay. So I can write IREF, okay, from here is IBF, and IBF is 15 I copy 1 by beta square plus 4 ICREF. Okay. ICREF is I copy 1. So I can get this equation. So from here I can find I copy 1 in terms of IREF and beta. So I copy 1 is IREF by 4 plus 15 by beta square. Okay. Similarly, I can find I copy 2 by saying that now this time IC ref is I copy 2 by 10. Okay. IC ref is I copy 2 by 10. Okay. So 4 I copy 2 by 10. Instead of 4 I copy 1, now I have 4 I copy 2 by 10. Okay. And here also copy 2 by 10 instead of copy 1. So this equation is again modified by using this relation, and from here I can find out I copy 2. Okay. So I copy 1 is this much, I copy 2 is this much. Okay. So both are different. Okay. And difference lies because of the emitter areas are different. Okay. So that is copy 2 is 10 times copy 1, which we have already commented here. Right. Copy 2 is 10 times copy 1. Right. So which is visible here also. Okay. So far we had seen NPN based current mirror. So similarly, PNP based current mirrors are also possible. Okay. And in fact, in a common emitter configuration, for example, this or maybe this. Okay. So we were using a current source, and then we said that instead of this current source, we can use a MOSFET, not MOSFET, a PNP BJT. Okay. So this PNP BJT act as a current source or load to this Q1. Okay. Now this current source can be replaced by a current mirror circuit. Okay. So this is my current mirror circuit using PNP transistor. So which can be used as a current source or load to my common emitter configuration. Okay. Or this common emitter configuration is biased by this current source, because this IREF, which is some good constant current source, it is copied over here. Okay. At the collector of Q1. Okay. So one of the major uh, use of current mirrors is that they are used for biasing, okay, purpose. So that is biasing this Q1. This collector current bias is fixed by using a current mirror on the collector. So current mirror act as a current source also here and also as a load. So for a NPN transistor, you will utilize PNP cascode for being used as a current source or as a load. Now for a PNP current mirror, that is this PNP current mirror that we had utilized in the previous case here, right? So this PNP cascode. So for this PNP cascode, this IREF, so this can again be generated via NPN cascode. Okay. So which has been shown over here. That is for generating a reference current over here at this point. So one can use a NPN cascode. So NPN cascode is used to generate a reference current, and that reference current is fed to the PNP cascode. So for this PNP cascode, my reference current is generated from the NPN current mirror. Okay. Not cascode, it is a current mirror, PNP current mirror, and this is NPN current mirror. Okay. So for PNP current mirror, reference current is generated by a NPN current mirror. Okay. Then we have already commented on this. That is, if I want this I copy 1 to be equal to IREF, then QREF and Q1. So they should not be discrete BJTs. They should be same BJTs. I mean, these NPN transistors should be exactly same. Okay. So otherwise there will be a mismatch in the saturation current of these two transistors, and there will also be a mismatch between the reference current and the copied current. Okay. So one has to make sure that these two transistors are same. Okay. Now, apart from having a BJT based uh, current mirror, so one can also think of using a MOSFET for making a current mirror, right? So the same current mirror circuit can be implemented by using a MOSFET. So for example, here M1 and MREF are MOSFETs. Okay. So again, gate and drain are shorted over here. So which will ensure that this transistor is always in saturation. Okay. And let us assume that M1 is also operating in saturation. So I can write the current I copy 1, that is drain current in saturation for M1. So I can write this I copy 1 is mu n CoX W by L by 2 VGS minus VT whole square. So here VGS is Vx, so I write Vx minus VT whole square. Okay. Similarly, I can write Iref, assuming that the collector current flowing into this reference transistor is equal to Iref, okay, because gate current is 0, okay, in this case. So Iref will be equal to the collector current, IC ref. Okay. So I can write Iref in saturation for this transistor. Again, using the same relation here. So mu n CoX W by L of reference transistor divided by 2 VGS minus VT whole square. So again VGS is Vx over here. Okay. So I get two relations. Okay. Divide 2 by 1. Okay. So when we divide 2 by 1, this goes off. Okay. So we have assumed that these two transistors are similar. So that means mu n CoX everything will be same. So they are gone. Okay. And this Vx minus Vt also goes off. Okay. So we are left with I copy 1 is equal to W by L of 1 divided by W by L of reference transistor multiplied by the current through the reference transistor. Okay. So now this copy 1 current will be equal to the reference current only when these two transistors are identical in shape also and size also. That is W by L ratios of these two transistors should be same. Okay. If the W by L are same, then I copy 1 is equal to Iref. Otherwise, the current will differ. Okay. So that is, if I want to scale this I copy 1, I'll have to increase W by L. So W by L of 1 should be greater than W by L of reference transistor. Okay. If I want I copy 1 to be greater than Iref. Okay. Similarly, W by L of 1 will be less than W by L of ref to make I copy less than Iref. Okay. Now similar to BJTs, we had seen that this kind of circuit is not a current mirror. Okay. So because X is now floating node over here. Okay. So in fact these two transistors are also not getting proper VGS. Okay. So this is not a current mirror. Now let us take some examples of current mirror scaling of the current. Okay. So let us say that I have a current mirror over here, right? So this part is my current mirror, this much, okay, a MOS current mirror, and to this MOS current mirror M1 is a load, okay, and then this transistor is also connected with M2 as a load over here. Okay. So I1 flowing through this and I2 through this. Okay. So that is, we are copying Iref on I1 and I2 as I1 and I2. Okay. Now if Iref is 0.3 milliamperes and the W by L ratio is such that it is 3 W by L, okay, for reference transistor, and for this transistor it is 2 W by L ratio, and this is 5 W by L. Okay, W by L is 5, W by L is 2, and here W by L is 3. Okay, so the current through this transistor, that is I1. Okay, so this will be 2 by 3 Iref. Okay. Just go back here and check here. I copy 1 is W by L of 1 by W by L of reference transistor multiplied by reference transistor's current. Okay. So this is W by L of 1 is 2 and W by L of reference transistor is 3. So this is 2 by 3 of Iref, that means. Okay. Okay. So I'll write here I copy is W by L of 1 by W by L of reference transistor multiplied by I reference. Okay. So in this case, for this transistor, it is, this ratio is W by L of 1 and W by L of RF is 2 by 3. Okay. 2 by 3 Iref, that means I1. Okay. And Iref is 0.3. So 2 by 3 multiplied by 0.3. So that is 0.2 milliamperes. Similarly for this W by L ratio is 5 by 3. Okay. So 5 by 3 multiplied by 0.3. So which is 0.5 milliamperes. Okay. So here we see scale down. The current has been scaled down from 0.3 to 0.2 milliamperes, and in this case it is scaled up from 0.3 to 0.5 milliamperes. Okay. So here scaling up and here scaling down. Okay. Within the same circuit, the current, the scaled up value and scaled down current values can be obtained. Now so far we haven't considered channel length modulation, so which can also be included, okay, by saying that lambda is not equal to 0 this time. So one can write the drain current equation I copy when and I ref by including lambda. Okay, so that is this part will be extra. Okay, mu n C ox W by L by 2 VGS minus VT 1 plus lambda VDS 1 minus VD sat. So finally, an I ref also can be modified by including this 1 plus lambda VDS term. Okay. Then I copy 1 can be calculated similar to what we had done for the previous circuit with lambda 0. Okay. So I copy 1 is now equal to this much. Okay. So this is similar to the previous equation, except this part is extra. Okay. So this part remains same and this part is extra, which is for considering the effect of channel length modulation. Channel length modulation. Okay. So with this I will stop here. Okay. And if you have any queries, then you can ask.